This is another nice application of the definite integral to find the length of a plane curve. And we'll go ahead and start by finding arc lengths. And the assumptions we're going to make here so that our integrals eventually will work out are the following. First of all, we'll assume that we have a function y equals f of x on a closed interval ab. That's nothing unusual. Here's what's new. We will assume that f prime, the derivative, is itself continuous. So f is what's called a smooth function. The derivative being continuous just means that the tangent line as it moves across the curve just changes at a nice continuous pace and doesn't alter very quickly. Note, f prime exists, the derivative exists, implies immediately that f is also continuous, in case we want to use that fact. So, what is the question here? The question is, what is the length, and I'll call it L, of the graph of f of x over that closed interval AB? Now that's something you may have wondered about. If you draw the graph of a function, is there any way to find the length of the curve that you've drawn? Turns out calculus, and in particular the definite integral, allows you to do that. And we're going to attack this in exactly the same way we've done everything else. What we do is we start off with a picture of some sort of a curve. Let's make it a very simple one here. This is y equals f of x, going from some point here A to some point here B. And we want to know the length of this curve. Well, what we'll do is we'll slice it up and approximate each piece by something nice. When we wanted area, we sliced up the area and approximated each piece by a rectangle. When we wanted volume, we sliced up the volume and approximated each piece by something nice, like a disk or a washer or a shell. Here, we're going to use line segments. So if I have a typical place from xk minus 1, say, to xk, and I take those slices up here, and all I want to do is approximate the length of this curve, why don't I approximate it by the simplest possible curve, which is just a line segment? And I will call that line segment there L sub k, L for length. Then, if I notice that I can draw a right triangle here, this distance here is just delta xk. It's just the width of what used to be the rectangle, but certainly is the slice. And this part up here, we can, if we like, call delta yk. Now, what is that? That's going to be the difference between the height up to the top part and the height up to this first point over here. So this height here would be f of, let's see, the point below is xk minus 1. And this height here would be f of xk, because xk is the point below here. And the difference of those two will be delta yk. So we're really not introducing anything new here. So we can start out by saying by the Pythagorean theorem, which applies to this right triangle, we see that lk squared, the hypotenuse of the right triangle, is equal to delta xk squared plus delta yk squared. So that's the Pythagorean theorem. Now we can replace the second part by the fact that delta yk is f of xk minus f of xk minus 1. And that's squared. Now, we'd like to simplify this. What we're going to use is the mean value theorem for derivatives to simplify this. And so we'll do a little side calculation to get this simplified, then come back to this. So this takes a little bit to do, but not too hard, I hope. Side calculation. So I'll just mark it like this. This is a side calculation. And imagine that we're looking at that curve on that little segment from xk minus 1 to xk. And in the middle here, we have the curve running like this. Now, if this is the f of x curve and it's continuous and differentiable, which we already know it is, then the mean value theorem says that if you connect the two endpoints here and get a line segment, that somewhere in here there has to be a place where the tangent line is parallel to the secant line. And that point is going to be some point xk star where that happens. And we wrote it out this way. We said the slope of the tangent line, which is the derivative at this point, the slope of that tangent line, is the slope of this secant line, which is the difference of the y values, f of xk minus f of xk minus 1, over the difference of the x values, xk minus 1. Well, this we already know is another way of writing delta xk, and if we bring this up to the other side, we can reverse this and write f of xk minus f of xk minus 1 equals f prime of xk star times delta xk. So we've taken this difference and reduced it to a single term, which is nicer, and now we'll apply that. So continuing our argument, Lk squared is equal to delta xk squared plus, and now we will replace that difference by f prime of xk star times delta xk all squared. Since delta xk is common to both of these and squared in both cases, let's factor it out. So this becomes 1 plus f prime of xk star function squared, and then delta xk itself squared on the outside. Now let's get back to Lk. This is Lk squared after all. Lk is the positive square root of all of this. So that's going to be 1 plus f prime xk star squared, and this becomes just delta xk. Then we do what we always do with integration, as we've seen. We go ahead and add these all up. This would be a line segment for each part of the curve. Add them all up and then take a limit as the maximum value of the delta xk's goes to 0. We will then end up with the length integral, which is the length of f over the interval ab. And that we'll just call L, and we'll write it as the integral from a to b of this square root 1 plus f prime of x quantity squared dx. And sometimes people prefer to write dy dx in here, squared. It's a little simpler to remember. Now, it was very nice to see how this developed from the calculus we know. However, frankly, looking at this integral with the square root and the derivative squared in here, it looks like one that's not going to be easy to do. And that's the case. Many times this integral is complicated enough that instead of actually calculating it out, we do an approximation of it. So you can keep that in mind. Also, there are variations on this. Suppose the function is not y equals f of x, but rather it's written in terms of y. The length integral might then be written, instead of having a to b, where a is x equal a to x equal b on the x-axis, we might go from y equals c to y equal d. We'll still have the square root of 1 plus, but instead of dy dx, we'll have dx dy, because here x is a function of y squared, and then dy in the end. But these are the sort of things that occur when you're actually working a problem, and you'll see what the function is in. Let's do one example of this, where the function actually works out so we can do the integral. Find the length of the graph of, and I won't write that out, x to the 3/2 power, y equals x to the 3/2 power on the interval 1 to 2. So here's a solution. And it's always useful in these situations to recall that long formula. The length is the integral from a to b of the square root of 1 plus dy dx quantity squared, all under the square root dx. So I'll need to find the derivative, square it, add 1 to it, then take the square root, and only then do the integral. So let's take this piecemeal. dy dx, y equals x to the 3/2. So dy dx is 3/2 x to the 3/2 minus 1, which is 1/2. So that means what's under the square root becomes 1 plus dy dx squared, which is 1 plus, if we square this, we get 9/4 x. So that means the length integral becomes the integral from 1 to 2 of the square root of 1 plus 9/4 x. Luckily, this one is not too hard. We can use substitution to do this. If we let u be 1 plus 9/4 x, then du becomes just 9/4 dx. That's easy. The upper limit, u at 2, becomes, we put the 2 in here for x, so that will give me 1 plus 9 halves, and 1 plus 9 halves will give me 11 halves. And then u at 1, we put the 1 in here, 1 plus 9 fourths, and that will give me 13 fourths. And there is my translation box. So I now get the integral. Because I have a 9/4 that isn't here, remember I compensate by putting a 4/9 out front. So I have 4/9. The integral from, let's see, the 1 is 13/4 on the bottom, 11 halves on the top. This becomes u inside, so this is u to the 1/2 power. And the dx and du are taken care of. And now we have an integral that's fairly easy to do. Let's just go ahead and walk it through a little bit on the next page. This is 4/9 times 2/3 u to the 3/2 as I integrate, going from 13/4 to 11 halves. And you can go ahead and do the arithmetic here if you want. What you'll end up with is something that's approximately 2.09. And I'll let you take a look at that. So keep in mind, the length integrals are often going to be complicated because of the square root and the derivative being squared, all of that appearing in the integrand. So don't feel bad if you are not able to calculate it. However, you should be able to set these up and to approximate them where appropriate.